Hey, what's up, guys? Today I'm going to discuss a very important topic of group theory and very basic one, that what actually a group is and how to check a finite set is a group or not. So I'm going to be very precise and simple. I'm not going very deep. I'm just covering the group definition with an example that how to check a finite set is a group or not under some operation using Callis table. So you can see a group definition. I have to read a pair G starix where G is a non-empty set and starix is a binary operation on G is called a group if the following conditions called axioms of a group are satisfied in G. So definition is very clear and simple that we a pair G starix is called group if it holds all the three mentioned axioms here. To start the axiom, we first have to make sure two things: what actually starix is and what actually this means that are satisfied in G. So we have to make clear these two things. First start with starix. Starix means operation. It may be addition, it may be multiplication. When we are going to apply groups axioms or a set, it must be under some operation. So we have to make sure what actually that operation is. We may check the group under addition, we may check a group under multiplication. So it must be one at a time. So before checking a set to be a group or not, we must specify what actually that operation is. It may be addition or it may be multiplication. And what actually this means that it is satisfied in G, this means closeness or closure. Closure or closeness means that every outcome must belong to the same set you are checking. You can see it further when I'm going to solve the example that what actually it means. Till now you have to make this understand that it must hold a property called closeness, not mentioned here, it is in the definition. So starting with the basic axioms, we have three basic axioms. The first is associative law. The second is very important and very basic, that is identity. And the third is again very important and very basic, called inverse. If you are checking a set to be a group under some operation, for instance, we say we are checking a group under addition. So what we have to do is to put addition symbol in place of starix mentioned in these three axioms, and to check, and we have to check these three axioms under operation addition. And if these three axioms holds under addition, we say that it is a group under addition. So in case of multiplication, we have to put multiplication symbols here, and we have to follow these three axioms under multiplication operation. And if these three axioms hold under multiplication operation, we say that it is a group under multiplication. So starix is just a symbol showing that it may be addition or multiplication. The first one is associative law. Associative law is very basic. If you have to, what you have to do is to take three elements here. A, B, and C are mentioned as general. You are going to take three elements A, B, and C from the group and check that this law, associative law, holds. That this left hand side and right hand side becomes equal for any ABC belonging to a set you are checking that it is a group or not. The second one is very important. If you take any element A from G, there must be an element E called identity element that doesn't change the element. That is, if we have an element A from a group and we have identity, in case of addition we have 0, and in case of multiplication we have multiplicative identity, and we will write 1 here. So what actually identity do? Identity doesn't change the element. It actually gives the same result after adding or after multiplying in case of different operations. If we are dealing with addition, then A plus 0 comes out to be A. And if we are dealing with multiplication, in multiplication we have identity equal to 1, then A multiplied by 1 gives us A. So the element must contains an entry, or you say identity element, that doesn't change the element. It actually gives the reflection, that is A dot E gives us A. So the second axiom is that your set must contain an element like this called identity element. The third condition is for each A belonging to G, that every element of your set must have inverse in it. What actually inverse is, in case of additive inverse, we have to say that if you have element 5, then it must contains minus 5, because 5 plus minus 5 equals to 0, that is additive identity. And in case of multiplication, we have multiplicative identity equal to 1. So if we have 5, then 5 cross 1 by 5 equals to 1. So your set must contain 1 by 5 as a multiplicative inverse of it. So every element A must have an element A inverse such that after commuting under some operation, it gives you identity. That is called inverse of that element. If these three conditions hold with closeness property, we say that that a set is called a group under that operation. It may be addition or it may be multiplication. Now moving towards what actually a billion group is. If all the above three mentioned axioms are satisfying for a set, and you check the fourth condition, and that is commutative law. Here A B belonging to elements of G. If these four conditions, three above one and fourth one this holds, then we don't have to say it a group only. We have to say that it is a billion group. If this fourth condition of commutative law holds for a particular set with these three axioms, we say that a group is not just a group, it is an abelian group. So after this definition and axioms, we are now able to check a set is a group or not using Calais table. So let's start our example. Here you can see what I have is a cube root of unity, and we are going to check that cube root of unity is a group under multiplication or not. You can see a small table here. This table is called Calais table, and this table helps us in case of finite elements, a group having finite elements, for applying checking that it is a group or not. So what we have to do, we have to write all the elements in the columns as well as row like this, and what we are and in which operation we are checking is that is multiplication, so we have to put the multiplication symbol here. And the next step is very simple. You have to just multiply these elements with these very simple basic multiplication, as 1 dot 1 gives us 1, 1 dot omega gives us omega, or 1 dot omega square gives us omega square. Similarly, omega dot 1 omega square, omega dot omega gives us omega square, omega dot omega square gives us omega cube. And you know, in cube roots of unity, omega cube is equal to 1. So I will write 1 here. Omega square dot omega 1 same, omega square dot omega gives us omega cube, and omega cube equal to 1. So I have written 1 here. Omega square dot omega square gives us omega 4, so omega 4 equal to omega cube dot omega, and omega cube equal to 1, so 1 dot omega gives us omega. So we are now done with Calais table, and this particular area is our outcome. So we are now in position to check that it is a group or not. So we have 5 mentioned axioms here, 3 of which already you know, that is identity, inverse, and associativity. And these 2 are extra ones, that is abelian and closeness. Closeness is very necessary. We first check axiom number 4, that is closeness. What actually closure is, you have to see that your outcome must in the given set you are checking. Like this, we have 1 omega square 1, omega square 1, and omega. You can easily see that all these elements are here. 1 is here, omega is here, and omega square is here. There is not a single element here that doesn't belong here. So the first axiom, that is closeness, holds. Now we'll move towards the second one, that is very basic and important one, that is identity. We must have an element identity. In case of multiplication, we must have an element 1 in a set. It is clearly seen that it has 1, but how to check through the table is again very simpler. But we have to see that are we getting a same row back? If we are getting a same row back, then the set must have identity. If we are not getting the same row back, then it may not have an identity element. Like this, you can see that our first row 1 omega omega square is exactly the same like above 1 omega omega square under operation addition when it comes with 1. So 1 dot 1 doesn't alter our results. It means that identity is here. 1 is here. You can see that our first three elements is exactly the reflection of same 1 omega omega square. So if we get our original element back, then it means that we have identity. So identity is satisfied. This axiom is satisfied. Now we coming towards the inverse. What actually inverse is, we have to multiply two elements and as a result we get identity. So then we say that these two elements are inverse of each other. So we have to find inverse here. In case of identity, inverse is always itself. So in case of identity like 0 and 1, their inverse are itself. The inverse of 1 is itself, the inverse of 0 is itself. So 1 dot 1 gives us 1, that is 1 itself. So inverse of 1 is 1. Now checking the inverse of omega, you can see omega dot omega square gives us 1. That is a multiplicative identity. It means that inverse of omega is actually omega square, and which is as it gives identity as a result, and it is there. Similarly, the inverse of omega square is omega square dot omega gives us 1. So the inverse of omega square is actually omega, as it gives identity 1 after applying the operation. So inverse is also satisfied. Now you can check the third axiom of abelian and associativity as well, that it holds or not, and let me know. Otherwise it's very simple and very general to check associativity and abelian. What you have to do is to take two elements from here given set and check its commutative law holds or not, and similarly you can take three elements from above and check associativity law holds or not. So here it is a very small and brief description of group and its definition. Hope so you liked it. Do let me know, and do like and subscribe. Thank you.